So our project is focused on parallelizing a collaborative filtering system and it is inspired by the Netflix challenge. So the Netflix challenge was an open competition to find the best collaborative filtering algorithms for Netflix to use to predict ratings for films. And collaborative filtering uses previous ratings to predict what users would want to watch. Began in 2006 and ended in 2009 and had a prize of $1 million for the winning team. So I'm other related techniques that involve in this. So as I said, there are recommender systems, and recommender systems predict what a user would rate a certain like movie or show, and it uses those predictions to give the users recommendations for what shows they would want to watch. There's also matrix factorization, which takes a matrix of ratings for a movie or for a user and breaks them down into a factor of its products, so into multiple matrices. And then there's alternating least squares, which fixes and solves these broken up matrices. And most of the time, these are item and user matrices. So a couple of related projects to this. There's one project we found that uses large scale parallel collaborative filtering. This solution used weighted lambda regularization instead of matrix factorization, and we found that this solution was not as efficient as we would have liked. And then there was also alternating least squares matrix factorization. Alternating least squares matrix factorization was done by Kevin and Yao, and it was really great because it helped solve issues with popularity bias, item cold start, and scalability issues. So Dr. Zhang gave us code with two programs. The first program is ratemovies.py, which reads in ratings and writes them into a CSV file. Overall, we didn't see many opportunities for parallelization here. There was also recommendations.py, which takes that file that was outputted by ratemovies.py and uses it to give it recommendations for the movies or users or so on. And we didn't see a great opportunity with parallelization for this option either. So that led us to implement our own solution. And our solution was inspired by Kevin Lau. It was inspired by a lot of what he did. It uses alternating least squares combined with the Spark libraries. And what we did is we used a profiler and ran it on our code and found that it would best work if we parallelized our grid search, specifically the call to the ALS train. And we did that for hyperparameter fine tuning.
So for our data sets for this project, we used the Movie Lens movie data sets provided by Group Lens. And so these data sets consisted of both a small and a full data set. In the most up-to-date data sets, those had 100,000 ratings and 27 million ratings respectively. The older data sets consisted of ones that had movie ratings in the amounts of 100,000, 1 million, 10 million, and 20 million. And so for the purposes of our project, we focused on using the ratings and movies files provided by these data sets. The ratings contained a user ID, movie ID, and movie rating. And then the movies contained the movie ID and title. And then data sets were kind of formatted differently depending on how old they were. So some of them were in CSV formats, some of them were in .dat, and then some were in data files. So we did have to customize our programs to accommodate those different formats. And the movies were read into Spark data frames, and the ratings were read into Spark RDDs. The ratings were randomly split into training, validation, and testing sets, and that was a 60-20-20 split.
Now I'll be discussing our planned method of parallelization. As mentioned in our project proposal, we plan to tackle the train ALS function as the primary area for improvement. We found this area through the C profiler, where we found that the train ALS function makes up for most of the execution time of the entire program. In the original version of the code, there's a nested loop that loops through different rank and regularization values. Each iteration of the loop makes a Spark API call to train an alternating least squares model with a unique combination of hyperparameters. The training of the model takes time, especially when using files with a large number of ratings. That means each iteration trains that model with that file with a large number of ratings. This adds up. Our idea was to utilize the multiprocessing library to allow the program to train models in parallel, specifically using either process or thread pools. This would cut down the execution time of the program by a lot. Unfortunately, as seen with the title of this slide, we ran into several problems with the implementation of the multiprocessing library, particularly with its usage of the Spark library. As said before, our program utilizes the Spark library and its functions, specifically the Spark data frame data type and resilient distributed dataset or RDD data type and the ALS training function. The ALS training function actually requires two different RDDs as input parameters, and due to the nature of how RDDs are constructed, they're unable to be pickled. This means that the RDDs are not able to be referenced in or broadcasted to other processes and can only be used on the driver process. Therefore, this prevented us from using the multiprocessing process pool module in any other library that utilizes separate processes. We experimented with trying to pass through and broadcast the Spark context, but we ran into similar problems as well. Fortunately, we were still able to utilize thread pools, but we knew that that would bring less benefit than process pools would have. Although we settled on thread pools for one attempt at parallelization, we also explored Python's concurrent executors module, as well as other threading options. These other options were not as applicable to the program though, and were not used. The image below shows the version of the trainALS function that is called by separate threads. Instead of taking an entire array of rank values, it now accepts a single rank value. Each thread maps a rank value to a function call of this train _ALS _parallel _2 function, and still loops through the regularization values. The rest of the function remains the same, and the function returns a tuple of the best model with that mapped rank value and its error value. When it returns back to the main function then finds the best model of the returned models.
Another method of speeding up the grid search we implemented was splitting up the work across multiple Python scripts and submitting those as separate Slurm jobs and submitting them all at the same time. And this way, although we wouldn't be using any specific parallel processing library, the work would still be done all at the same time in parallel. And so we achieved this by altering the trainALS method to only run once with a specific pair of parameters. This enabled us to run all the method calls to trainALS with different hyperparameters all at once on different Beocat nodes. So we can take a closer look at the original Python script and the new split up version for this parallel method that we implemented. As you can see here, the original Python script has different hyperparameters, the ranks and regularization, in an array, and it uses those arrays in a nested for loop and calls trainALS sequentially. However, our new parallel method simplifies trainALS to only call it once with specified parameters, and the execution of these method calls are controlled by a mass bash script, which loops through the different hyperparameters and passes them to the Python script as command line arguments. This fires off an entirely separate Python script for each call of trainALS. And then looking at the controlling bash script closer, we can see the actual flow of execution. So there's a mass bash script that controls the execution of the separate Slurm jobs. And as you can see here, similar to the original Python script, this bash script uses a nested for loop to iterate through the pairs of parameters. And within that nested loop, it calls the Slurm scheduler to start a job for a Python script. And then it also keeps track of each job number and job status. And so the Python script, shown in blue here, writes the parameters it used and the mean squared error of the model it trained to a file called results.txt. And another, again, emphasis here on the fact that all of these Slurm jobs are being run in parallel on Beocat. After starting all of the jobs, this bash script loops through the jobs and job statuses. And if any of them are still in a queued or running state, it loops through it again and updates the job statuses. Once all of the jobs have finished running, this bash script calls another Python script to iterate through the results.txt file and find the best parameters that produced a model with the least error, and then it prints out these parameters to the console. Afterwards, the script does some cleaning up and is finished executing. So although in theory this is a suitable method for speeding up grid search, there are unfortunately several drawbacks for this method. First, there's more overhead required to run each Python script because each script reads in its own copy of the movies and ratings files. And in our sequential script, this data was already loaded in and cached. Additionally, because there are 35 separate scripts running at once, this does consume a lot of memory and resources. And because of this, the performance of this method is highly dependent on the current available resources on the Beocat nodes. So for instance, if there were a lot of other students using nodes that we wanted to use, our jobs would be stuck in the queue, and that would not be ideal for what we would want. Also, if any Slurm job fails for some reason, this would interrupt the flow of the controlling shell script and mess up the entire program. Finally, unlike the sequential grid search, there's not an easy way to save the best model since we're running these Python scripts separately. So instead, we are required to retrain the model with the fine-tuned parameters that are determined and printed out at the end.
For the testing, we ran the jobs on Beocat with different variations of nodes and cores. As seen in the side image, we tested the program with a single node in either 1, 2, 4, 8, or 16 cores. We also tested the program with 16 cores spread across either 2, 4, 8, or 16 nodes. In addition to testing the program with different hardware, we also tested it with different number of ratings. Each job reads in the entire file of 20 million ratings, but utilizing the Spark data frame and its limit method, we were able to specify how many ratings will actually be used for each job. The number of ratings range from 10,000, 100,000, 1 million, 10 million, and 20 million ratings. For evaluating the results, we utilized the time module to measure execution time. We then implemented the ps-util library to measure CPU usage before and after the train ALS call, as well as the program's memory usage across different jobs. To give a little background on how we will be running the jobs on Beocat, we will be using Beocat nodes confined to ELV's node cluster, which has the following: 2 times 8 core Xeon E5-2690 CPUs, which have 2.90 GHz base core clock frequency and 20 megabytes of Intel Smart Cache. They also have CentOS Linux 7. We will be using Linux version 3.10.0, Python 3.7, and Spark 3.0. To specify the different number of nodes and number of cores, we will be using the end tasks and nodes restrictions on the job. Now I'll be discussing the results we currently have, starting with the data from the jobs ran with a single node and different core counts. As seen in the images on the slide, the results between the original program, labeled grid, and the program with thread pools are quite nearly the same, with the differences in execution time being quite negligible. This is actually what we expected when we were forced to use thread pools instead of process pools. Python has its global interpreter lock that states only one thread can be executed at any point in time. This means the inclusion of thread pools, which we did, would essentially be useless. However, thread pools can be useful when tasked with problems that are I/O bound. Unfortunately, the Netflix recommendation system in ALS training, which is what this program is heavily CPU bound due to the sheer number of computations. So due to the CPU bound nature of the problem in the Python global interpreter lock, these results were expected with their thread pools. Spark already does its own partitioning and separates Spark API calls into separate processes to reduce single process workload. So that's why you can see quite drastic improvement when increasing the number of cores in both versions of the program. If we were able to implement the multi-processing process pools as we initially planned alongside Spark, we would have likely been able to see much larger speedups from the program. Since we were also unable to bypass the Python global interpreter lock due to the usage of Spark and Python that also restricted the usefulness of thread pools and increased execution time. Our results for the jobs with various numbers are incomplete and therefore will not be shown in the presentation, but the results suggest that more cores on less machines provide better results than the same number of total cores spread across more machines. This is also expected due to no message passing interface being utilized, which means there's no point in using more nodes, as well as the CPU bound nature of the program, which means more core power is better. The graphs below show the CPU usage percentage after the train ALS call minus the CPU usage percentage before the call. Besides a few strange outliers in both graphs, the graphs for both the original program and the thread pool version of the program follow the same trend, in which case the difference increases with the number of cores used. This makes sense mostly because with more cores being used, it would make sense that more of the CPU is being used as well.
Now that we've discussed the results from using thread pools as well as using different numbers of cores, let's briefly go over some of the preliminary results from using the split up Python scripts and controlling bash scripts on the small dataset, which again consisted of 100,000 moving ratings. So looking at the runtime of the sequential code, we see that the average iteration of a call to train ALS is 7.78 seconds. And then the total runtime for the entire sequential grid search is 306.33 seconds. So when considering the parallel version that we previously discussed, if we're able to execute all iterations of train ALS completely in parallel, we would expect a speedup equivalent to the number of iterations, which is 35. However, after running the parallel version of our program, the actual runtime differed from these expectations greatly. The average iteration of a single Python script, which again called a single iteration of train ALS, was 48.98 seconds. The total elapsed runtime of all these scripts, which did run mostly in parallel, was 62.32 seconds. So in this particular instance, there were enough free nodes on Beocat to run all these scripts in parallel. However, we cannot always guarantee that this will be the case. And so in the end, the actual speedup of this parallel implementation was only about 4.9 times the original total runtime, or 4.9 times faster, excuse me. And we predict that the reason of this is, again, due to the overhead required to load in and parse the movies and ratings files on each Python script. Because the sequential version only loads in this data once, it is able to perform faster on each iteration. However, in this implementation specifically, it's being loaded in 35 separate times in each Python script. So the memory and computing power it takes to load in these files separately ultimately slows down the execution time of the program. And we will present full results on or across all the other data sets in the write-up of this report as well.
So in conclusion, we believe we were overzealous with our initial planned implementation. Python's global interpreter lock and Spark's restrictions prevented us from finding a simple way to parallelize the program. The program is clearly CPU bound and not IO or memory bound. This clearly corresponds with the results where thread pools did not provide a benefit to the program, but it is interesting that different node counts saw improvement with thread pools. So for future work, for the final report, we will continue testing the program with separate jobs for each combination of hyperparameters. Our other future work could include an in-depth implementation of alternating least squares and its corresponding API from scratch. We could also experiment with coding everything from scratch in a different language. This could be C, C++, Python, but they'd have to not include a global interpreter lock. Here is our works cited and some links to some pictures that were used. Thank you for watching our presentation.